We have seen in the previous lectures that when there is a voltage difference between 2 points, it causes current to flow from higher voltage location to lower voltage location. And that's true for both positive and negative charges. If you are confused why negative charges moving in the upwards direction should cause current flow in the downward direction, I would suggest you to rewatch lecture 6. Okay, back to the point. I was saying if there is a voltage difference, there should be a current flow. But actually, that's not entirely true. Because if you can just somehow trap the charges so that they can't move, there wouldn't be any current. Because if the charges can't flow, that means there's no current, even though there is a voltage difference. So it's not always true that if there's a voltage difference, there should be a current. So we need to make sure that the charges are free to move, otherwise there wouldn't be any current. But since in this example charges are not trapped and perfectly free to move, we do get a current flow. Let's just say we are doing this experiment in vacuum. So there's nothing to prevent the charges from flowing anyway. Now let's take a better look at what's really happening here. So how do you think the charges are moving exactly? Do you think they're moving with constant velocity like maybe 5 meters per second? Or are they accelerating and their velocity keeps increasing every second? The answer is they will accelerate through the vacuum, meaning their velocity will keep increasing the whole time. In fact, if we just let them fly through vacuum under voltage difference like this, it will keep getting more and more velocity forever. Now the next sensible question should be, why would they accelerate? There are two ways you can explain it. One way is to understand that the charges are moving because they are feeling a force due to the voltage difference. And according to Newton's law of motion, when a force is applied on any object, it creates an acceleration. And acceleration means the velocity should keep increasing. The second way to understand this would be to use the energy bars we introduced in lecture 2. You will see why I am preferring this second explanation in the next lecture. This explanation goes something like this. When the charges are moving from one location to another, their potential energy is also changing. In fact, these charges will move in such a way that their potential energy keeps decreasing. That's because every object tries to minimize their potential energy, even negative charges. If you need a refresher, watch lecture 4 again. So, by moving from one voltage to another, their potential energy decreases. But remember, the total energy needs to be kept the same. For keeping the total energy constant, the charges increase their kinetic energy, while their potential energy keeps decreasing. Since increasing kinetic energy means increasing velocity, the charges keep accelerating. So in summary, their potential energy decreases and kinetic energy increases, which in turn increases their velocity. That's what happens when charges are moving freely through vacuum. Now let's try to look outside of vacuum and charged objects. See if we can find anything interesting. What would happen if we applied a voltage difference across a neutral object? After all, neutral or not, every object is made up of protons and electrons which do carry charges. So the voltage difference might have some effect on neutral objects after all. When you apply a voltage difference across an object, in most cases nothing interesting really happens. That's because even though they contain charged particles like electrons and protons, they are not free to move. The protons of the atoms are arranged in a strong crystal structure in the object, so they can't move at all. The electrons do want to move towards the higher voltage region, but they are also strongly bound to their parent atoms. So their orbits get slightly pushed towards higher voltage, and that's it. Nothing else really happens, because the atoms don't let go of their electrons, like responsible parents don't let go of their children. And like I mentioned earlier, if charges are not free to move, then there will be no current. These types of materials are called insulators, materials that don't allow charges to flow through them. For example, plastic, rubber, wood, brick, glass, etc. are insulators, and if we apply voltage across any of these, we won't get any current. But that's not the only type of material. There's another type of material whose protons are bound to their positions like insulators, but their electrons are fairly free to move. So those electrons can move from one atom to the next. As a result, if you apply voltage difference across these types of materials, electrons flow from lower voltage to higher voltage. Since the electrons are negatively charged objects, they cause current flow in the opposite direction. These types of materials are called conductors. Metals are common examples of conductors. So when we apply voltage across metals like copper or aluminum, current flows from higher voltage to lower voltage. There's another type of material called semiconductors, which are in between insulators and conductors. But we will not talk about them in this course. You will learn them in CSC 251. For now, we will restrict ourselves to just insulators and conductors. In fact, we will mainly focus on conductors. So let's simplify what's happening when we apply a voltage difference across a conductor. Electron on the leftmost atom moves to the higher voltage region, but that creates an empty space. The next electron sees an opportunity to move closer to the higher voltage, so it jumps to the next atom. That in turn creates another empty spot, causing the next electron to move to its position. And this system keeps propagating through the whole conductor. All of this happens really fast, and that's why we use electricity in the first place. Still, the electrons have to stop at every atom even if it's for a fraction of a millisecond. But from outside of the conductor, this is what it looks like. We just observe a current flow from higher voltage end of the conductor to the lower voltage end of the conductor. In the next lecture, we will discuss how the charges will move through the conductors. Are they accelerating like in the case of vacuum, or will they have a limit to their velocity?